This presentation describes Fresnel's half-period zones. We discuss the construction, elementary description, and final conclusion of Fresnel's half-period zones. It is shown that the amplitude contributed due to the whole wave is just half that due to the first zone acting alone. Let us construct Fresnel's half-period zones as follows. Let us find the effect that a slightly divergent spherical wave will produce at a point ahead of the wave. Consider the figure on the left. B, C, D and E represent a spherical wavefront of monochromatic light traveling to the right. Every point on the sphere may be thought of as the origin of secondary wavelets. We wish to find the resultant effect of these at the point P. In order to construct Fresnel's half-period zones, we divide the wavefront into zones by the following construction. Around the point O, which is the foot of the perpendicular from P, we describe a series of circles whose distances from O measured along the arc are such that each circle is half a wavelength farther away from P. If the distance OP is equal to B, then the circles will be at a distance of B plus lambda by 2, B plus 2 lambda by 2, B plus 3 lambda by 2, and so on till B plus m lambda by 2 from P. We know by Huygens principle that every point on the wave is sending out secondary wavelets in the same phase. These will reach the point P with different phases since each has traveled a different distance. The phases of the wavelets from a given zone will not differ more than pi since each zone is on an average lambda by 2 farther away from P. It is clear that the successive zones will produce the resultants at P which will differ by pi. The difference of half a period in the vibrations from successive zones is the origin of the name half-period zones, since lambda by 2 corresponds to a phase difference of pi, which corresponds to T by 2 half a period. We now begin the elementary discussion of the division of a plane wavefront into half-period annular zones. W represents a plane wavefront moving to the right. In order to find a disturbance at P, the wavefront is divided into annular zones as follows. The central zone extends as far as M1, where M1P is equal to MOP plus lambda by 2. The second zone extends to M2, where M2P is equal to M1P plus lambda by 2, which is basically equal to MOP plus lambda. Thus, if MOP is equal to B, the jth zone extends from Mj minus 1 to Mj, where Mj minus 1P is equal to B plus J minus 1 lambda by 2 and MJP is equal to B plus J lambda by 2. Continuing from the previous slide, we can see that the area of the jth zone is obviously given by pi mjmo square plus pi mj minus 1 mo square, which translates to pi b plus j lambda by 2 whole square minus b square minus pi open brackets again b plus j minus 1 lambda by 2 the whole square minus b square. Simplifying the above expression, we will get pi open brackets b square plus 2b j lambda by 2 plus j square lambda by 2 whole square, giving you lambda square by 4 minus b square. The second expression translates to minus b open brackets b square plus 2b j minus 1 lambda by 2 plus j minus 1 square lambda square by 4 minus b square. When we simplify this, we will get, for the first expression, pi open brackets b j lambda plus j square lambda square by 4. For the second expression, minus b j minus lambda plus j square minus 2j plus 1 lambda square by 4. The b squares have all mutually cancelled out. Continuing from the previous slide and simplifying the expression further, we find that the resultant expression comes out to be bj lambda plus lambda square by 4 open brackets j square minus j square plus 2j minus 1 close brackets, where we have gathered together the terms common to lambda square by 4 minus bj lambda plus b lambda. Simplifying this, we will get this equal to pi open brackets lambda b plus lambda square by 4 2j minus 1, which is equal to pi b lambda after neglecting the second term. So we find that areas of all zones are approximately equal. We now show that amplitude contributed due to the whole wave is just half that due to the first zone acting alone. If we represent by AM the resultant amplitude of light from the mth zone, AM will have alternating signs because changing the phase by pi means reversing the direction of the amplitude vector. When the resultant amplitude due to the whole wave is called A, it may be written as sum of the series A equal to A1 minus A2 plus A3 minus A4 plus and so on, where the last term will be minus 1 raised to the power m minus 1 AM. Now, three factors determine the magnitudes of the successive terms in the series. Number one, because the area of each zone determines the number of wavelets it contributes, the terms should approximately be equal, but should increase slowly. Number two, since the amplitude decreases inversely with the average distance from P of the zone, the magnitudes of the terms are reduced by an amount which increases with M. Number three, because of the increasing obliquity, their magnitudes should decrease. Continuing with our summing of the contributions from the various half-period zones, we may thus express the amplitude due to the mth zone as Am is equal to constant times Sm upon dm 1 plus cos theta, where dm is the average distance to P, theta the angle at which light leaves the zone, Sm the area of any zone. We've already shown that the area of each zone is approximately constant. This means that the ratio Sm upon dm is also a constant independent of m. Therefore, we have only the obliquity factor which changes for each zone. The obliquity factor causes successive terms in the series for A to decrease very slowly. The decrease is slow at first due to the rapid change of theta with m, but the amplitudes soon become very nearly equal. With this knowledge of variation in magnitude of terms, we may evaluate the sum of a series by grouping its terms in the following two ways. The first way is A1 by 2 plus open brackets A1 by 2 minus A2 plus A3 by 2 plus open brackets A3 by 2 minus A4 plus A5 by 2 and so on till we come to plus AM by 2. Or we can group the amplitude terms as A1 minus A2 by 2 minus open brackets A2 by 2 minus A3 plus A4 by 2 minus A4 by 2 minus A5 plus A6 by 2 minus and so on till we have the last two terms as minus AM minus 1 by 2 plus AM. Now grouping the amplitude terms, supposing M is odd. Since the amplitudes A1, A2, etc. do not decrease at a uniform rate, each one is going to be smaller than the arithmetic mean of the preceding and the succeeding terms. Therefore, the quantities in the parenthesis in the above equations are all positive and the following inequalities must hold. We must have A1 by 2 plus AM by 2 less than A, which is in turn less than A1 minus A2 by 2 minus AM minus 1 by 2 plus AM. Because the amplitudes for any two adjacent zones are very nearly equal, it is possible to equate A1 to A2 and AM minus 1 to AM. The result is A is equal to A1 by 2 plus AM by 2. If we take M to be even, we will find by the same method that A comes out to be equal to A1 by 2 minus AM by 2. Hence, the conclusion is that the resultant amplitude at P due to M zones is either half the sum or half the difference of the amplitudes contributed by the first and last zone. Finally, if we allow M to become large enough for the entire spherical wave to be divided into zones, then theta approaches 180 degrees for the last zone. Therefore, the obliquity factor causes AM to become negligible and the amplitude due to the whole wave is just half that due to the first zone acting alone. We now carry out a vector addition of the amplitudes. These are going to be alternately positive and negative. And normally, we would draw them along the same line, but for clarity here, we are separating them in a horizontal direction. The tail of each vector is put at the same height as the head of the previous one. The resultant amplitude A due to any given number of zones will be the height of the final arrowhead above the horizontal base. And in the figure, it is shown for 12 zones.